So to start off today, I want to do a really quick overview because we're kind of in the middle ground right now where we're moving a bit ahead on material that's not going to be on the exam. And so I don't want to go too crazy so everyone will forget. So I wanted to go through the general outline of the Felder and Rousseau book, which kind of is the same format in the class that we're following, and sort of contextualize where we are and where we're going and how the exams all fit into there. So chapters 1 through 3. I would call this basically just background and definitions. This is where we talked about unit conversions, unit systems, hydrostatic pressure, right? General engineering, content, and materials. In chapter 4, this is really where we got to the interesting stuff for the class. And this is material balances. And this could be for reacting and non-reacting systems. We also talked about single versus multiple units. And so this is the content that is going to be contained within exam, whoops, I can't write, exam 1. This is what we're going to be looking at on Friday. Units, hydrostatic, single phase properties, and for the most part, material balances. Now, we spent the most of our time on material balances, so most of the exam is going to be covering that content there. But, as I've mentioned in passing several times, these problems are somewhat contrived, right? You're given the concentration of stuff coming in, you're given the concentration of stuff coming out, you're given the flow rates and all that kind of stuff. And so everything is kind of lumped into these design specifications. And so what we're going to be doing moving forward is getting away from design specifications, and you're going to be calculating what the actual outlet conditions are going to be based on real properties. So if we sort of draw a line here, and chapter 5 is sort of a little bit saddling both of these, but for the most part, the lion's share of material for exam 1 is lumped up in chapters 1 through 4. So chapter 5, this is single phase properties. And for this, we've talked about liquids, ideal gases, and non-ideal gases. And that's what we're going to be continuing on after this brief recap. But everything's single phase. A single phase of liquid, a single phase of gas, and what are the properties? What this allows us to do is to relate between the pressure, the temperature, and volume. So we don't have to always have molar flow rates or mass flow rates. You can get it in whatever types of units you'd like. Chapter 6 is where we will spend a lot of time. This is multi-component, multi-phase. This is going to comprise of exam 2. So we are going to spend a lot of time talking about multi-component and multi-phase calculations. So what this allows us to do is instead of saying, oh, the top flow rate is 90% component A and 10% component B, we're going to actually calculate what the thermodynamic concentration of the separation is going to be. And so we're going to spend a tremendous amount of time on chapter 6, where we're basically going to have to go through and sort of teach basic multi-phase thermodynamics. The next step in the process, chapters 7 through 9, this is energy balances. So in chapters 7 through 9, this is where we're going to figure out, okay, so let's say we can do a process. How much energy is it going to take? What is the temperature of the inlet streams versus the temperature of the outlet streams? Is this reaction endothermic or exothermic? Let's say we have 15 simultaneous reactions going on. Do I need to put energy into the reactor or take energy out of the reactor? Right? These are all the topics we're going to be covering in energy balances. So the first early chapters, like 7 and 8, this is going to be where we're going to review your thermodynamics material. How do you choose reference states? What is enthalpy? What is internal energy? How do we calculate it? And then moving on to energy balances of non-reacting systems. This would be for like a distillation column, right? If you have a vapor coming out of the top and a liquid coming out of the bottom, what's the net amount of energy? And then lastly, energy balances of reacting systems. How much energy do you get for burning a liter of gasoline? Or what is the temperature of a methane flame burnt in oxygen versus the temperature of a methane flame being burnt in air? Right, so those are calculations we'll do for energy balances. And then, I think depending on the edition, this might change a little bit, but basically chapters 10 or 11, I'm not quite sure, I don't remember if it changed. We're going to be talking about transient systems. In this case, accumulation is not equal to 0. So we're going to redo basically everything we've done already, but instead we're going to have this time-based differential, right? du dt, dm dt. What is the mass changing of the system as a function of time? What is the internal energy of the system changing as a function of time? Right? So we're going to break down that steady state assumption, and we're going to look at ordinary differential equations of our material balances. Right now we're neglecting the time-based effect, but in the future, at the end of class, we're going to be looking at differential equations to solve all these things. So we're going to redo everything, but from a calculus perspective. So hopefully that provides a little bit of context. So as I mentioned, we're kind of in the middle of things right now. Everyone's looking to exam 1. But let's do a quick recap of non-ideal gases. So the general idea that I had broken it down into is that we have the ideal gas law, and we want to improve upon it. And the 3 strategies that we talked about, we talked a little bit about the cubic equation of state, but our 3 strategies are to improve the assumptions, improve ideal gas assumptions, and this would be specifically the excluded volume, and interactions. And this led us to what we call the cubic equation of state. EOS, equation of state, cubic equation of state. The second strategy would be to add in plus minus corrections. And this leads us to the Virial Equation of state. I don't know if you guys still have your handouts that we passed out on Friday, or rather Wednesday last week. We have all these equations of states listed. And then lastly, we talked about sort of these times divide corrections. And this corresponded to empirical approach. And this is your compressibility factor.
Does it say interactions?
This one says interactions.
Right above it, is that interactions as well?
This is corrections, and this is interactions.
No, right above it.
Interactions.
Okay.
Yes, yes. Okay, so for those of you who brought your handout, this will be a little bit more fun to look at it for this particular lecture here. So these are the strategies that we'll cover to talk about how do we get more accurate calculations. Now, we discussed the van der Waals equation of state, which is a cubic equation of state. So this is still recap from what we covered through on Wednesday. This is the van der Waals equation of state. V-A-N-D-E-R-W-N-A-L-S. Van der Waals equation of state. It was the first cubic equation of state. It was the first equation of state that could predict the existence of liquids, but it is not very accurate. So on your handout, if you look here, you have the van der Waals equation of state, where the A and B parameters are given as a function of the critical properties, TC and PC. And then we have two other ones here, the SRK and the Peng-Robinson. They are much, much, much more mathematically complex, right? For example, if we look at the Peng-Robinson equation of state, let's say, for example, you have this alpha term, which has the kappa term, and the kappa term has this omega term, right, on the second to last equation there. So it starts to be a little bit tedious to calculate this. So I would never, ever, ever recommend anyone do this by hand. Always use a spreadsheet, right? Even a calculator is tedious to apply these equations of state, right? So it's much easier if you have a spreadsheet and you have the omega term, which goes into this term, which goes into this term, which goes into this term, makes it a lot more complicated. Yeah?
What is the omega term in that one?
Good question. We'll cover that in just a bit. That's the eccentric factor. So we'll cover that in just a moment when we go into the details of one of these. Okay, but let's look at the general structure of a cubic equation of state. It's called cubic because if you look through it and you kind of cross multiply, you'll end up with a volume term to the third power, right? So that's why they call it cubic. The ideal gas law has volume to the power 1, right? So this is a lot more non-ideality functions built into it. All right, V minus B. What does this minus B term account for? As a reminder for what we talked about on Wednesday.
The volume of the gas particles.
Exactly, the volume of the particles of gas themselves. In the ideal gas law, we assume that that is 0. Right? The density is so low and the volume of the container is way, way, way bigger than the volume of all the gas particles. But as you compress a fluid really close together, as you get close to like a liquid density, then the volume of those particles really matters. Right? Because the density between a solid and liquid is very similar for most materials. Right? So the only difference is that in a liquid, there's really compact spacing, but they kind of tumble and roll around. But the density is not that much difference. Right? There's the amount of void space in a liquid is very small. In this A term, what does the A term represent? Interactions. So, if my gas molecules are attracted to one another, what kind of effect would we expect that to have on pressure?
Lower pressure.
Lower pressure, right? They have less desire to hit the wall and more to kind of stay in the mixture. So how would that correspond to an A greater than 0 or less than 0?
Great.
Right, so if A is greater than 0, that means attraction. A is less than 0, right? That means we have a negative and a positive. That means our pressure is going to be higher, right? This is going to be repulsion. And depending on the density that you're at, you can have your particles either be attractive or repulsive, even for the same exact conditions. Right? Because you can imagine if you get your fluids really close together, you're going to start to have those electron clouds overlapping and they're going to want to push each other apart. Right?
Would attraction mean they're like reacting?
No, not necessarily. It just means that, so we'll go a little bit into sort of molecular interactions here. So the reason why like molecules want to be near each other is in the case of something like water, for example, right? You have a really strong polar end and a really strong positive polar and a really strong negative polar. And those kind of line up like magnets of sort, right? So it's kind of easy to visualize that in a sense like with a polar molecule. But when you're talking about a non-polar molecule, let's say we have like pentane, right, which is just 5 carbons in a row. Those electrons are not very mobile, but they're a little bit mobile. Right, so you'll have a carbon, so you have carbon, 1, 2, 3, 4, 5 of them. And so you have electrons that'll somewhat gently slosh over here and somewhat gently slosh back. Right, that's called your London dispersion or your van der Waals interactions. Does that sound familiar? People have heard about that? Okay, so most everyone. Now, the reason why pentane likes pentane, but pentane doesn't like water, for example, is because the frequency at which those electrons kind of slosh back and forth is going to be exactly the same for every pentane. So it just happens that the molecules will line up because some of the electrons will be down here on one and some of the electrons will be over there on others. And so you'll have very slight positive and very slight negative regions. So like molecules are always attracted to one another, unless you get them so close that the electron clouds start to overlap, in which case you have Coulombic or electrostatic repulsion by the negative charges of the electron clouds. But the reason why everything is attracted to itself is because every molecule has sort of a natural frequency that these electrons want to go sloshing back and forth in between. And that's why you have a net attraction. So in general, this term is always going to be positive unless you get to extremely high densities, or if you have, for some reason, very dissimilar materials. Right? So in general, molecules are going to be wanting to attract to one another, not repel. Otherwise, everything would sort of fall apart naturally. But that's sort of the fundamental picture of why that would be the case. Now, to go into a few more details, we're going to break down, let's look at the, well, so I don't necessarily, I'm super keen on writing down the cubic equations today. Who doesn't have their handouts? All right, so look over a shoulder, I guess. There's a couple of key properties here. So in the SRK and Peng-Robinson, SRK and Peng-Robinson equation state, what we need to know to solve the problem is we have A is a function of TC and PC. B is a function of TC and PC. In addition, we have this alpha term, which is a function of TR and kappa. We have kappa, which is a function of omega. Right, so instead of writing out all the equations, we kind of just follow along as we go here. Do we all remember what the critical temperature and critical pressure are? Right, this has to do with the phase diagram. TR, this is the reduced temperature. So if we look at our phase diagram here, okay, this is pressure on our phase diagram. This is temperature. What phase of matter are we in here?
Yeah, solid.
Solid. Low temperatures, high pressures. Down here, gas. Actually, I will write it here as vapor, because technically it's not a gas until you're over here. Here, liquid. So one sort of a semantic discussion. If you pressurize a fluid and it can condense into a liquid, then it's going to be a vapor. If you pressurize a fluid and nothing changes, that's going to be a gas. So nitrogen is a gas, water is a vapor at our normal conditions, right? Because the critical point of nitrogen is a very, very, very low, like 100 Kelvin or something like that. This point right here, triple point, we watched that demonstration video of tert butyl alcohol at the triple point where you had freezing, boiling, and liquid all existing at the same time. And here is our critical point. So this point right here is TC, and this point over here is PC. Now the reduced temperature and the reduced pressure, TR is equal to temperature over the critical temperature, and the reduced pressure is equal to the pressure over the critical pressure. So what we are employing by using these equations of state is something called the law of corresponding states. So what the law of corresponding states says is that every fluid behaves the same, not as a function of their temperature and pressure, but as a function of their reduced temperature and their reduced pressure. Right? So it's saying the only reason why nitrogen behaves differently than water is because nitrogen is a supercritical gas that's above its critical point, whereas water is a subcritical fluid that exists mostly in the liquid state at some temperature and pressure. So what this is basically saying is that everything behaves according to this exact phase diagram. Yes?
Sorry, could you explain, like, word for word what the law of corresponding states was again? What you said earlier? It was-
So let's see if I can summarize this without giving us a long novel. Basically it says every material I think that's pretty concise. Every material behaves the same as a function of TR and PR. So not of the actual temperature and pressure, but of the temperature and pressure that are important to that fluid, which is how far or close is it away from the critical point. Now, for the most part, the equations for A, B, alpha, and kappa, to some extent, these are empirically derived. Now, they have a theoretical foundation, right, which is saying, okay, if I accounted for excluded volume or what types of interactions, but a lot of these numbers that you see here, like in kappa, it's, 0.4851 plus 1.552. A lot of these can be empirically, they just fit a bunch of stuff. So they just based their equation of state on a particular class of fluids. Let's say it's simple hydrocarbons, right? And most of these equations of state were developed for oil and gas and for chemical research, and so they care mostly about commodity chemicals, right? So different equations of state will be slightly better for different types of fluids. So most of these terms are empirical. Now, the one material that I would like to talk about is the eccentric factor. And this omega term right here, this is called the eccentric factor. Now, the most common way that I've heard the eccentric factor described is it accounts for how non-spherical the molecule is, right? And that if it's non-spherical, let me go over here, I've got a bit more space. They say it'll behave a bit differently. But I don't particularly like that example. So for example, if we have a compound, carbon disulfide versus carbon dioxide, right? They're both linear, non-polar molecules, right? So if the eccentric factor were to somehow account for whether or not it's a spherical, a linear, or a planar, or a different type of molecule, we would expect that these two compounds should have fairly similar eccentric factors. But in fact, they don't. This one has an eccentric factor of 1.09, and this one has an eccentric factor of 0.239. Not anywhere close. Instead, the eccentric factor has a strict definition mathematically. Minus log. Excuse me. Has a very strict mathematical definition. It is the negative log minus 1 of the reduced saturation pressure at a reduced temperature of 0.7. Super cool, right? What does this mean? What this basically means is that this line right here, this is called the vapor pressure. We write that as P vape, or we'll just write it out here, vapor pressure. The vapor pressure is the pressure at which a fluid will boil at. So if I am right here at some temperature and pressure in the liquid phase, if I want to boil this liquid, I can either drop its pressure, cross the vaporization line, or I can keep the temperature up and I boil it like we would do on our stovetop, right? Because you can boil water by either pulling a vacuum on it, right? I'm sure you guys have all seen this in maybe a chemistry class, or you can boil water by heating it up, which I hope most everyone has done in their real life. So, the vapor pressure is an important material property that we will be spending a tremendous amount of time on. So don't worry, don't get your hopes up. So if we have a reduced temperature of 0.7, according to our eccentric factor, we want to know what the vapor pressure is here. This will give us P sat at TR equals 0.7, right? A TR of 0.7 is basically 70% of the way from absolute zero to the critical temperature. we can get some vapor pressure measured off at that particular value. So all the eccentric factor is basically some anchor point right here that basically tells us what is the shape of this vapor pressure curve at some point near our critical point. Probably more detail than most people wanted. Yes?
So for like PR and TR,
Mhm.
that.
These ones down here, right?
Yeah,
Mhm.
so big P, big T, that's like, could that be any temperature or pressure? So if your system's at 25 degrees Celsius, it would be, the reduced temperature would be the temperature of your system over the critical temperature?
Correct.
Okay.
Well, you would have to do it in Kelvin though. So for example, the
Okay.
critical temperature of water I think is around 600 or 650. And so we're at about 300 now. So our critical or reduced temperature for water is about 0.5, how we are right now.
Okay,
and I
the
believe-
temperature changes based on the temperature of the
Yes.
system.
So if I increase the temperature of my water to 400 degrees C, above its boiling point, its reduced temperature would be, I don't know, 3/5 or something like that. Yeah, so it would go up. It follows it up. Okay. So in order to talk a little bit more about reduced temperatures and pressures, it helps to transition on to some other fluids. So basically, for the purposes of our class, these non-ideal equations of state, we're mostly going to use them for saying, okay, if we assume it's an ideal gas, this is the pressure in the tank, how much material is in it, right? But that's not really how real gases behave. In your Thermo 2 class, you will be using these equations of state for everything. This phase diagram right here, you can develop this phase diagram from an equation of state. But I swear to you, it is a lot of work. And that's all the fun stuff you get to do in Thermo 2. But for our class, not so much. So instead, let's move on to the virial equation of state, which actually has a theoretical foundation. It's something that is a topic I discussed in my graduate level thermodynamics class. But for the purposes of this course, we don't need to go into the actual derivation of it. But in general, the virial equation of state is one where it accounts for not the excluded volume, but the interactions between particles. So the virial equation of state is going to be good for non-ideal gases that are far away from the point that they're going to condense into a liquid phase. So we typically write it as PV over RT is equal to 1. This is exactly the ideal gas law, right? PV equals RT if you times it over to the other side of the equation, right? And we typically will write this as Z, which is the compressibility factor, right? So if Z is less than 1, we have a negative deviation from the ideal gas law, which means that the pressure is lower than the pressure you would predict if it were an ideal gas.
What does that say, sir? This is
Which one? Positive, and then quotation marks for deviation.
Thank you.
So what we're going to be doing in the virial equation of state is we're going to account for multi-body interactions or attractive and repulsive interactions by adding in correction factors to the equation of state. So for the virial equation of state, oops, let's see, let me write this. Z is equal to PV over RT. So I can get rid of this here. This is equal to 1 plus correction factors. B over V hat plus C over V hat squared plus. This is the second virial coefficient. This is the third virial coefficient. This is the fourth virial coefficient, and so on and so forth. These are just correction factors. we will always truncate it there. The virial equation of state truncated at the second virial coefficient. And from your handout, you can see that we take a similar approach. We also assume the law of corresponding states to apply the virial equation of state. And you can see that these terms, B, right here. So B is actually a function of t, and this is equal to RTC over PC B0 plus omega B1. And we have equations for B0 and B1, which are listed on your sheet. This is also on Canvas and everything there. Right, but what we're assuming here by applying the virial equation of state is that everything is behaving the same as a function of its reduced temperature and its reduced pressure. So same thing that we applied earlier. Now the virial equation of state is actually not cubic, it's only quadratic. So it actually cannot predict the existence of liquids. So I'll write that down. Cannot predict liquid properties. Rather, it can't even predict that liquids exist, much less get their properties correct, which means this is good for fluids So this one's good for fluids that are farther away from the liquid state. But it's much more complex, it's much less complex than the SRK and the Peng-Robinson. Maybe a trivial amount less complex, but it's not as accurate as well. Right? It can't even predict the existence of liquids. Okay, so you will have to use these two strategies, but I think that the one that is most commonly going to be used to solve practical problems is the compressibility factor, which we'll talk about next. Yes, question?
If you truncate it off at the third or fourth, then would it be able to account for liquids?
Possibly, although customarily it's not done to do that. Because I think if you look at a generalized form of the cubic equation of state, you may be able to argue that if you truncate it here, you effectively have a cubic equation of state functionality. So in theory, yes, mathematically you could. I don't know how extreme this coefficient would have to be. But in general, according to how the virial equation of state is derived, this should have a smaller effect than this does, according to the derivation approach. But in terms of practically speaking, if you use that functional form and then just made up numbers for C, yeah, you could make a liquid happen. But in the derivation, these are sort of like a Taylor series expansion, where you get to less and less important contributions. So in the true form of the virial, not really. But mathematically, yes, it could look similar. Okay, now the one that most everyone is going to use for real problems is going to be the compressibility factor. And the reason why I say most people are going to use it is because it is by far the easiest to apply. Factor. All right. Low percentage chance that I'm going to get everything spelled right here. Okay. So in this sense, we're going to use this term Z, which we already defined as the compressibility factor, which is equal to PV over RT. And quite frankly, it is as simple as reading it off a chart. So in front of you, you have a series of handouts. There's a series of graphs, right? You've got 1, 2, 3, and they're all at different ranges. But they all will have the same general structure, where here they have Z on the y-axis. On the x-axis, they have PR, which is our reduced pressure, P divided by PC. And then we have a series of lines, and I'm just going to draw this bottom one on the back page. It looks something like this. And so on, and yeah, not very good drawing, but something like this. Each of these lines here have some TR label. TR is equal to 1, TR is equal to 1.1, and so on and so forth. So this is sort of our introduction to engineering charts. The goal of an engineering chart here is to cram as much information on it as possible. So, the key thing and the most straightforward way to use a compressibility factor is if I know T and P, I can use the chart to look up Z and then calculate V hat. Right, so let's run through this really quickly in our head. I don't have an example with actual numbers. But if I have a fluid at some temperature and pressure, I can calculate its reduced pressure by dividing by its critical point. So we would have to also look up what its critical point is. So let's just say that happens to be right there. I also have a fluid at a particular temperature, which means I can also calculate its reduced temperature, which means I'll then trace this line up here, see where it intersects. Let's say, for example, it's a TR of 0.1. I draw the line over here, and this gives me my Z value for the system. I take the Z value, I plug it into here, and I can calculate my density of the fluid or my specific volume. But you can also go backwards, right? If I know my density, but I don't know my temperature, I can still solve the system, but I have to do it a little bit iteratively, right? I have to guess for a temperature, to guess for this, to guess to see if everything lines up. Right, so there's a lot of ways we can use this. So if you're doing something that's a really straightforward application, if you know the pressure, you know the temperature, it's trivial. But if you're having to do an iterative process, right, trying to see if I guess a temperature here that calculates the right Z so that it lines up perfectly here, right? So for example, if I have a situation where I know my V hat and P, right? My unknown in this case is going to be temperature. So what I would have to do is I would have my V and P here figured out. I would have to guess a temperature, calculate a Z, and see if that Z intersects at the same PR. If that doesn't work out, I have to go back and I have to guess another temperature, and you can see how you can go back through and iteratively solve this problem. Or if you use the Virial equation of state or a cubic equation of state, it's just one nonlinear equation you have to solve. Right, so the charts are convenient unless you have to use them for their non-traditional sense, and then it's really kind of a painful process. You'd much rather just have an equation you can solve for T, or solve for T, or solve for V, or whatever the cases you're solving for. Yes?
Sorry, so you said that when your densities are right, or PR is given, then you can look at your Z value.
So if you know, this is the most straightforward application. If you know your pressure and temperature, you can calculate your PR and you can calculate your TR. And then you can directly read what your Z is, and then you can directly calculate what your V is. But in order for us to know our compressibility factor, we would have to know the temperature or the pressure. So if either of these two terms are unknown, then you would have to iteratively make sure that all of the conditions are satisfied to get everything to line up perfectly, so that your Z intersects with your TR line, intersects with your PR line. And there's only going to be one condition that that's satisfying in. So you'll have to play around a little bit with it. And so this is where it's kind of a give and take, you know, how much is it worth to you to use the compressibility charts versus coding up an equation of state or some other strategy to estimate what's going on.
Thank you.
Mm-hmm. Yeah.
So there's 3 of these charts. Which one do we use for which situation?
Very good question. Let's look at the ranges then. So let's start on the first one here. And the first one on the main page here, it goes from a Z of 0 to about 1.5 and a reduced pressure all the way up to 35. Or actually, no, maybe higher than that. It's a log scale, so 30, 40, almost a reduced pressure of 50. The top one on the next page, we have a Z going from 0.4 to 1 and a reduced pressure going from 0 to 1. And on the bottom one, we have going from 0.2 to 1.2 and a reduced pressure going to 0 to 10. So depending on where you are in that fluid's reduced pressure and reduced temperature, that tells you which one to use. So for example, we can see here that most all of them, at least on this back page here, the ones you'll be using mostly, your Z is less than 1, meaning most molecules are attracted to one another. Now the only time when you get a Z that is greater than 1, right, here we go. So Z is less than 1, negative deviation, right? That means things are pulling themselves closer together and they're pushing less on the wall. When Z is greater than 1, that means they are pushing each other apart and you have a pressure that's higher than you'd expect. So, based on that, would we expect to have more repulsion, right? So in other words, a positive deviation at high pressures or low pressures? High pressures. At high pressures, the molecules are really, really forced to be near each other. And so that sort of general attractiveness that these molecules have to one another, that kind of isn't enough to keep them close together, right? You start to get overlapping electron clouds. And when those electron clouds start to overlap, it doesn't matter how much those two molecules like each other, the electrons take control and say, no, we got to get further apart. And so if you look at your compressibility chart, particularly the bottom one on the back page, you can see a general increasing trend in getting a Z of greater than 1 as you get to critical pressures above about 6 to 7. Right? And that's really where you're cranking these molecules close together. Right? That's extremely high pressure. We're talking megapascals or gigapascal pressures. Now, these charts that you're looking at, they are developed for ZC, right, the critical compressibility factor, which we define as PC over RTC, right? So it's all the critical parameters put together as equal to 0.25 to 0.29. I think these charts might have slightly different ones here. If you look at the front one, it says this one's made for a compressibility factor of ZC equals 0.27, this first page here. But basically what they're saying is we're going to assume everything behaves exactly the same and we can just rely on that. Again, another application of the law of corresponding states here. Everything behaves the same as a function of the reduced parameters. All right, a few minutes left. Let me swap this out. So in terms of accuracy versus ease. So over here, we're going to say it's easy, and this is difficult. Which of these is going to be more accurate? Easy calculations or difficult calculations? Typically difficult. So this is going to be accurate and less accurate. So what is the easiest calculation we talked about with single-phase fluids? Ideal gas law. Ideal gas law is going to be the easiest but least accurate. Okay, of the next three that we talked about today and Wednesday, which do you think is the next easiest to use? Compressibility. Next, Virial Equation of state. And then lastly, we have the cubic equation of state. But I will also add one more. What is more accurate than a cubic equation of state?
SRK.
So SRK, Penn Robinson, are already equations of state. How would you get the most accurate property value of a particular fluid. Let's say density of water at some temperature. What's the most accurate way you can think about to get it? It's table or measurement. So experimental measurement. So I would argue that despite the complexity of the Peng-Robinson or the SRK equation of state, I'm willing to bet that if I asked every one of you to give me an estimate of the density of ammonia gas at a pressure of 15 atmospheres and a temperature of, I don't know, 200 degrees C, I'm willing to bet you would do that a lot quicker using one of these complex equations of state than actually going to the lab and measuring it. Right? Sir, I don't care how complex the equation is. Right? Unless it takes you weeks or months to evaluate, it's going to save you time than actually doing the experimental measurements itself, which is going to be by far the most accurate. So depending on which stage you're at in sort of designing a process or developing something, you'll probably start off, maybe you'll even start off with ideal gas law or compressibility factor. Maybe you'll start off with cubic equation of state. But by the time that a multi-billion dollar plant is built, you're going to make sure that every single property that is needed for that process is going to be measured experimentally. And that's a lot of times what industrial research labs will do, is they'll just measure these properties for different companies. A couple of very minor comments. When you apply the compressibility factor for hydrogen, look in the book, there are some correction factors. You can't exactly use the TR and PR because hydrogen is so different from a gas. You have to like add and subtract a few different terms there. Just a couple of things there. And also for mixtures of molecules, so if you're trying to calculate the properties of mixtures, especially for the compressibility factor, we can use something called K's rule, in which case you calculate some Tc prime So essentially what you're going to do if you have a mixture, you'll just take a mole averaged critical temperature and mole averaged critical pressure to give you these effective critical pressures and temperatures for mixtures. And then the reduced parameters are still the same, but instead you use these averaged critical points to make your calculations. Now the last comment I want to go through today is, why is it always critical temperature and critical pressure? Because those are the two easiest measurements to make. Right, so if we have a tank of a fluid, either we have to super accurately know what the volume of it is and what fraction of it is filled, and then we could estimate the density, or we could just slap a pressure gauge on it and put a thermometer in there. Right, so temperature and pressure are the easiest variables for us to measure, which means that they're the easiest variables for us to control. So that's why generally we'll always be going from temperature and pressure conditions, calculating what the volume or density of the fluid is. Sometimes you'll have to go backwards. Mathematically, it's exactly the same, but you can see, especially with the compressibility factor that I've hidden away here, right, they're designed to make it so you go from temperature and pressure to density. So you go from the easiest to measure variables to the least easy to measure variables. All right, so Wednesday will be exam review and then exam on Friday. Office hours the same. See ya.